Hey guys, welcome to another video here for Algebra 2, and we're going to be starting a new chapter of material here today, actually talking about two different types of graphs, but they're so similar, they're so related, that we put them together under one bigger umbrella. And so the letters here for this target are going to be E and L, and those two things kind of talk about an exponential type of function and then a logarithmic type of function. And they're actually related because they are inverses of each other, which is something that we just talked about in the past target. So currently, we're hoping that you guys can graph exponentials and logarithms and see a lot of the patterns that kind of go into them. They're one of the last functions that we discuss because the pattern has a pattern to it, which is kind of a meta thing to say, but the pattern changes. It depends on actually another parameter, if you will. So let's go ahead and let's talk about some basics. All right, there are two different types of exponential functions. There's exponential growth, and then there's exponential decay. And it's helpful to kind of see the difference between the two. So I made a little Desmos graph to kind of show you that it's all about the base. It's all about what number that exponent gets attached to. And so for our first example here in the notes, the base that we are going to graph right away is 2 to the x power. And so that's the example I have pulled up at the moment. The base here is 2. 2 to the x makes a graph that kind of starts off very low, I suppose, close to the axis, and gradually works its way up and up and up. And if I were to zoom out, you can see that it increases quite rapidly. Now, what if I were to change that to maybe be a 3 for a base, or a 4, or a 5? Can you see what's happening to the graph itself? Okay, hopefully you're noticing that it's getting stretched further and further. It's growing maybe more rapidly. And I kind of gave away what type of exponential this is. Now, eventually we get to this point where the graph seems to go in the other direction. Okay, so I'm moving my slider around and I'm getting bases that are fractional. Okay, so between 1 over 10 as a base and maybe 10 as a base, you can see that they're pretty similar, but they're going in opposite directions. They're starting very big and decreasing down to be very, very small amounts, or they're starting pretty small and then they're growing to be larger. And so if you notice what types of numbers those bases would be, smaller fractions, think about numbers that would be less than 1, are going to decay. They're going to shrink and get chopped up into smaller and smaller pieces as you go, versus numbers that are larger than 1. Even if the base is like 1.05, that's 21/20ths. I know that's not very much over 1 itself, but it is gradually growing. And so it might take a while, might take until 60 or 70 or 80 or 90 before it starts to turn the corner. But if I zoom out, you can see that exponentials grow so quickly. They are really like the rocket ship of the math function world. Now something actually interesting happens at 1 itself. 1, because you're multiplying by 1 and 1 and 1 and 1 again, is actually the tipping point between growth and decay. It's the divider between those two subfamilies, if you will. And so 1 itself is just the line y equals 1. So back here, a graph is considered to be growth if the base is larger than 1, if it's over 100%. It doesn't matter if it's 1.01, that is just a smidge over 1, and so it will continue to grow faster and faster and faster, always multiplying by 101%. So you can kind of deduce that a graph would be considered exponential decay if the base would be between 0 and 1. Notice I'm leaving the negatives out of this definition. So what happens if the growth or decay factor is less than 0, if it ends up being negative? This is really interesting to see. It's something we'll talk about later. So let me go ahead and instead of having the base be like positive 2, let me go ahead and let's change that to be negative 2. And it's quite interesting because the graph blows up. It explodes into smithereens. You can see the traces of some of these points, and they seem to follow like a growing pattern, but none of these points are connected. And what's wild about this, I don't know if I'm going to be able to get it to show up or not, is that there are actually points that are below the x-axis as well. And so what happens when you take -2 as a base and multiply it by itself once is you end up with a -2 answer. Maybe put an exponent in here. Okay? But if I take that exponent and now I make it a 2 instead of a 1, now I'm getting a positive answer. What if I make it a 3? Now I'm back to the negatives. What if I make it a 4? Now I'm back to the positives. And so the whole thing kind of tears itself apart because you're multiplying a negative number over and over again, which sometimes gives you positive answers while other times giving you negative answers. And the graph just can't cope. Becomes what mathematicians would call discontinuous. It cannot continue on one solid connected curve. That's why it blows up. So the answer to that third question is that the graph explodes into smithereens. And maybe a good example here to jot down would be that -2 to the first power is -2, while -2 squared is 4, positive 4, and then -2 cubed is -8. And so the answers to this particular type of base will switch from being positive to negative, to positive to negative, to positive, and just back and forth, back and forth. All right, we won't do any of those, but it's good to understand that bases themselves, what the exponent is attached to, cannot and should not go negative for us. So let's take a look at our first graph. Down below, we have a table of values that we're going to do a little bit of work to find the y values, the outputs for these x values, and we can choose whatever we want. I think it's nice in most cases to choose some x values for the exponent up here that are negative. I like choosing 0, and then maybe going into the positive, so 1 and 2, and we could even fit in a third positive value here. So in our work, this is going to be its base 2, here is the base, raised to the -2 power. And if you recall from when we worked with exponents and the rules for exponents, that negative exponent just means that 2 squared is wanting to live below. It doesn't like being in the numerator of the fraction. And so we would fill the numerator in, since it's blank, with a 1. And so 2 squared on the bottom is 4. This is 1/4, which is equal to 0.25. So that is my y value, 0.25. So I'm really creating this point. Here's my x value, here's my y value. Left 2, and up 1/4 of a box. Not very far. Now we can go ahead and we can do -1. So taking 2 to the -1st power. Doesn't like living there. Wants to live in the bottom as 2 to the 1st. So 1/2 to the 1st is just 1/2. That is 0.5 as a y value. So -1, comma 0.5. Left 1, up 1/2 a box. Now we can go ahead and we can do 0. 2 to the 0 power, anything to the 0 power actually, is 1. That's one of those special rules that we come across occasionally. And so I'm really dealing with the point 0, comma 1, as opposed to -1, 0.5, and then -2, comma 0.25. Those are the points we're graphing. And this point is actually a very special point. It's called the initial value. It's where this graph starts initially from the center of things. It has an initial height of 1. After this, we can go ahead and do 2 to the 1st, which is just 2. So that's 1, comma 2 as a coordinate over 1 up 2. We can go ahead and do 2 to the 2nd power, make our x value into a 2, and that's 4 as an output. 2 as an input, 4 as an output, 2, comma 4. Going back, we can do one more. 2 to the 3rd is good. We end up getting 8. So 3 as an input leads me to 8 as an output. Notice all of these x values are giving me one particular y value, which is a good thing. It would be strange potentially here to get multiple answers from one input. So now we can go ahead and we can start to see that curving upward action. But you'll notice, if I go back to to Desmos here maybe really quick. Change that back to an X and make sure my base is positive. On the left-hand side, I didn't really dig into this very much, but it seemed pretty flat. If I go ahead and zoom in on Desmos, you can notice that there's actually a gap here. And as we learned in the rational chapter, this has a special name. When we start to approach a value as we go further and further out, that's called an asymptote. And if I were to zoom way out into the thousands, the negative thousands, it's very, 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 very close to 0, but it's not quite 0. It will never actually equal 0. And that's because you're always going to be dividing more and more up, as we'll see here in a second. So on the left, close to the asymptote, rising through these points, faster and faster and faster and faster. If you wanted, it's a pretty good habit to go ahead and along this axis, we can put a dashed line for our asymptote line. So now, how are we going to graph this? What pattern goes with this? Okay, and we'll see here in a second that I really like putting my distances. Okay, so I'm thinking about easier ways to graph this than doing an XY table. Okay, it takes too much time, it's too much effort. So let's go ahead and let's write the height from the asymptote that each of these points would have. This first dot was a quarter of a box high, so 0.25. This next dot, the light purple dot, is 0.5 as a height. Then I had a height of 1, then a height of 2, then a height of 4, then a height of 8. Okay, and so I'm just trying to measure how far it takes to get from the asymptote to those individual points. And I'm sure you can start to see that as I move to the right, I am multiplying by 2. And that should make sense. We're taking our base and we're multiplying it over and over again. This is 2 times 2 times 2. That's what 2 to the third is saying, that idea. And so every single time we're going to double, we're going to multiply by 2 the prior height that we were standing at. So 8 as a height would lead us to 16 next, 2 to the fourth. 16 leads us to 32. We're doubling that. That's 2 to the fifth. Then 64, and then 128, and it gets really big really quickly, doubling every single time. Now, what if we, instead of moving to the right, had to move to the left? Going this direction is the backwards operation, so going from 32 to 16, from 8 to 4, from 4 to 2, from 2 to 1, to 1 to 0.5. Every step going left is not multiplying by 2, but it's multiplying by 1/2, which is the same thing as instead of multiplying, dividing. So instead of multiplying as we go to the right, we would divide by 2 as we go to the left. And so you can see that the pattern that goes with this is repeated multiplication and repeated division. Now this graph overall is an example of exponential growth. That's because my base is larger than 1. I'm doubling every single time. And that's really the pattern for this particular function. So what if we go ahead and we look at the second problem? G of x here is 1/2 to the x. As I said earlier, this is going to be a decay graph because, multiplying things by 1/2 and multiplying things by 1/2 is going to make it smaller and smaller and smaller and smaller as we go. And so testing out some x values, we could test out the same set, -2, -1, 0, 1, 2. And so if I go ahead and take 1/2 and I raise that to the -2 power, what we can do with this is distribute that negative in to each part of our fraction. 1 to the -2 power and 2 to the -2 power. Well, neither of them particularly like living where they're at. So this jumps to the bottom, this guy jumps to the top. And so I'm really left with 2 squared in the numerator and 1 squared in the denominator. They were, jealous of where they were. So the bottom likes to be in the top, and the top likes to be in the bottom. We end up getting 4 over 1, which is 4. What that says is if I go left 2 and up 4, okay, those inputs and outputs have that location in space. What about our next x value? Taking 1/2 to the -1 power. We can do the same idea. We end up getting 1 to the negative 1, let me space that out, over 2 to the negative 1. And those don't like the part of the fraction they're sitting in. So we're jumping. That's what I like to call it. Those things are going to equal 2 to the first on top over 1 to the first. 2 over 1. And that is a final result of 2. As a point, going left 1 and up 2, negative 1 comma 2 lives here. Now we can go ahead, we can take 1/2 to the 0 power. And anything to the 0 power is 1, so it's a great value to choose, so I'm dealing with the point 0 comma 1. Then 1/2 to the first. Well, anything to the first is just itself, so I end up getting 1/2. So 1 comma 1/2 out of that. Over 1 up half a box. And then the last one is 1/2 to the second power. And just like with the negative exponents, we're going to distribute that in. So I get 1 squared over 2 squared. Nobody needs to jump. They're perfectly fine where they're at. And so 1 squared is 1, 2 squared is 4. So that will be the coordinate 2 comma 1/4. So going over 2 and up just a little bit of a box. If I'd wanted, I could do 3. So 1/2 to the third power is 1 to the third power over 2 to the third power. So that ends up being 1 over 8. 1/8, if you like decimals, is 0.125. That's not very much of a box, just a smidge off of the x-axis, but you can really start to see the curve coming in here. So just like in the last one when I talked about distances and distances from the asymptote to the curve, we can talk about those here. 4 is a distance, 2 is a distance, 1 is a distance, 0.5, 0.25, 0.125. And so you can kind of see, as I move to the right, I am again multiplying, but I'm multiplying by our base. I'm multiplying by 1/2. A pretty important idea is that our base really is our pattern. It tells us what to multiply by as we move to the right of the graph. If I multiply by 1/2 again, I'm going to get 0.0625. So every time, half as much, half as much, half as much. Okay, it's like cutting something in half if you have to split between you and someone else, like a candy bar. Cutting it in half and repeatedly cutting it in half leaves you with less stuff each time. Now what if I had wanted to go backwards? Well, I could multiply, 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 but instead of thinking about this as multiplication, I could say it's the same thing as dividing by 1/2. If you divide by a fraction, it's the same thing as multiplying by its reciprocal. So multiplying by that reciprocal would be multiplying by 2 over 1 instead of dividing by 1 over 2. So the pattern with these is really based off of how far it takes to jump from the asymptote to the individual points. And you have to kind of understand growth or decay based off of those. So think about what would have come prior to having 4 as a height. Okay, 8 would have had to come next because you cut that in half. What would have come before 8? Well, 16 has to come before that because you cut 16 in half to get the 8. And then before that, you would have to have 32. And so you can kind of see you're multiplying or dividing. Both of those things are very, very similar. And now we can go ahead and we can try to draw our curve in. Remember, as I go further now to the right, I'm never going to hit the x-axis because there's always a little bit to cut in half. There's always something left over, no matter how small. So what patterns are really created by these functions? Okay, well, those patterns, as we kind of discussed, are all based on distances. You don't have to write this word for word, but this is what we're saying. The distances that the graph is from the asymptote, how far the curve is from the asymptote. Both multiply by the base as you move to the right, and divide by the bases as you move backwards and to the left. And you can kind of switch those ideas a little bit if you understand decay and how decay works. If it's a fraction that's less than 1, that is division. So under that, what do you notice about the graphs as we go further to the left for the first graph, or if we go further to the right for the second graph? What are we approaching? So we kind of discussed that you're getting closer to the x-axis, but that's because there is an asymptote at that x-axis. You will never touch it. And then it asks us to consider f of x, so the first graph here, okay, 2 to the x. Is that growth or decay? Well, because the base is over 1, and because the distances between our asymptote and the graph increase as we go, this is growth. You are doubling in height, doubling your distances every time. The second graph, which was called g of x over here, that is a graph of decay because your distances are decreasing. They're getting cut in half from 16 to 8, from 8 to 4, from 4 to 2. And so that is a decay graph because the base is a smaller fraction than 1. Okay, you always have to compare this to 1. So maybe a few things to jot down as well would just be back up here that this is exponential growth. You are growing from the asymptote from left to right, versus this second graph is decay because your distances decrease. They decay from left to right. So let's go ahead and let's flip to the next page and let's talk about how these exponentials can be written. There's actually an extra letter in here that we don't use for a lot of the other types of functions. And you'll notice it's going to have the letter b. And that's actually what the exponent is attached to. And so b here, that is going to be our base, which it's nice that base and b start with the same letter. But that really describes our pattern. As we saw on the front page, if it's a 2, we are doubling as a pattern. If it's 1/2, we are cutting in half as a pattern. It tells us if we are growing or if we are decaying. So growth or decay. This is a really big deal. It's one of the first things that I look at when I come across an exponential. Then a few of the other important players. The a value, just like everything else from this year, is going to be our stretch and compress. Okay? Even if we are growing, we can compress the graph and make it a little bit shorter from what it would be naturally. This will also take care of our reflection. Now, mathematicians would actually call that position the initial value. It's very important. It's what we initially start with our graph. So that is an important term to know. Then we have our good old friend h, which is our horizontal movement. Notice it's up here in the exponent spot, and so that's going to move us left or right. It's backwards, just like everything else we've learned so far this year. When x has something close to it, it's going to behave backwards from what you would expect. And then we have k. Okay here. K is going to move us up or down. So you have to be paying very close attention to the size of the numbers that we're going to be putting in. Is it small as an exponent, up in that superscript position, or is it a larger number that's written at the end? Sometimes we'll put parentheses around it, and sometimes we won't. So let's go ahead and let's take a look at how these things work with the patterns that we kind of discovered here on the front. Question number 3, r of x. Okay, let's talk about a few of these things. First is that my initial value in front is a 1. That means when I start, I'm going to start 1 box away from the center of things. Well, the next question would be, where is the center? So if I look, I have a +1 up in the exponent position. That's going to move us left 1. Then I have a +2 at the end, and that's going to move us up 2. And so what we are moving when we do these graphs, just like rationals, is we're not moving the curve itself, we're moving the asymptote. So the asymptote kind of shoves the curve around. This is almost like our new origin. It's relocating things, if you will. So left 1 and up 2, I typically like to put a star there, just like rationals. We put a star. That's where we're starting. But from here, do I grow or do I decay? Well, that's where this base comes in. If my base is equal to 3, that is going to be growth. Okay, so down below we have some qualities that we would want to describe. This is exponential growth. I'm going to be tripling. So for this particular graph, I can go ahead and put my asymptote in. It is, for an exponential, always horizontal as an asymptote. It's like the ground. And so we're going to be jumping off of the ground in a pattern that triples. Okay, having a base of 3 tells me that I'm tripling instead of doubling. So from here, let's go ahead and let's write out some distances. What is the initial distance from the star? Well, right up here, that initial value was a 1, and so I need to jump 1 away. So that A value can stretch to maybe instead of being 1 away, being 2 away, or being 4 away if it's stretched by 4 in front. But if there's not a number, it's just the default. It's a 1 boxer. So from this, I need to make sure I'm tripling. So I'm going to take 1, I'm going to multiply it by 3. Okay, and this is the trick. This is the pattern you can do so you don't have to go through an XY table. I wish I had known this when I was in high school. So from this asymptote, I'm going to jump 1, 2, 3 boxes. That is my next point. Then I take this distance and I multiply by 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 would be 81. If I kept multiplying, you can see that we get pretty big pretty quick. 243 is my next triple. So 9 just fits. Notice I'm counting from the asymptote. Oops. It's just a smidge off the graph. So 9 from 2 puts you at a height of 11. 27, the next point over, is just crazy far. It's off the page. Now, this is not good enough. I have 3 dots, and those are all going to the right. Again, this is because I multiply by 3. So how could I go left? How can I get points that came prior to our initial value? Well, you just have to divide by that base. So I divide by 3 going this way. And that makes sense. To go from 27 to 9, you divide. To go from 9 to 3, you divide. So what would have come before? 1? Well, just 1 divided by 3. That is a third of a box. It's not very far off. As a decimal, that's 0.3333 forever. Then I divide that by 3 and I get 1/9, which is 0.11111 forever. Okay? And it's helpful to see, I'll show you a few tricks in your calculator, but the decimal value visually shows you it's getting smaller. 1/9 divided by 3 is 1/27, which is a very small decimal amount. And if you give me 3 or 4 points to the left, 3 or 4 points to the right, I'm usually pretty happy. So we can draw our curve in, taking care to not cross the asymptote and to gradually rise up through those points. Now, we haven't talked about domain and range. So the domain here, the x values that this graph uses, well, it goes left forever, and it is continuing to go outwards to the right. It will have heights further and further and further out in that direction, and so it is going from negative infinity to positive infinity. If you would like, you may certainly put all real numbers there. Now the range, the y values, is not the case, going down and up forever. This graph is cut off so that there is nothing down below, for this particular example, down below the asymptote. And so that height, the height of 2, is kind of this natural cutoff. It's the floor of this function. And so there's nothing down in here. And so when we go ahead and we do our range, we have to talk about it living from 2 to infinity. It does go up forever. Now what do I put on 2? Okay, do we ever reach this asymptote? Well, the answer to that would be no. It's always going to be 2 and a little extra. It's always a smidge away. And so we cannot stand on 2. We cannot put a bracket on 2. We need to put a parenthesis on that 2. All right, so our range is limited for an exponential. Our domain is unlimited. Let's go ahead and let's take a look at number 4, b of x. Good old Barry. Barry here has a 1/4 as its base. Okay, if I want to talk about that first, maybe here, that base being 1/4 tells me that I am to k. Okay, that means I'm going to be dividing by 4. I'm chopping it into fourths. I got really good at doing this in my family because we had 4 kids, and so anything that we had to share among all of us, I had to cut it up. And the cutter always has to choose last, and so you get very good at cutting even-sized pieces, because if you make one bigger than the other, somebody's going to take it before you ever get to choose your piece. And so cutting into fourths is something that makes a lot of sense in my brain. But what about some of the other transformations? -2, that's up there with the x minus 2 moves us right 2. And then -3, because it's at the end, is the k value, and that's moving us down 3. So right 2 and down 3. That's going to be our new origin, if you will. It's our starting point. We can go ahead and we can actually even put the asymptote through that starting new origin point. That is y equals -3. I either have to be above that or below that. Those are my two choices, one side of the fence or the other. So now, how do I get the curve from here? Well, we got to look back, and my initial value in front is 1. So IV here is the initial value. That means from this star, I just jump 1. Because it's positive, it's going to be above. What do I do with that 1 height now? Well, I need to cut it into fourths. So 1 cut into fourths is a fourth, multiplied by a fourth here. Then I'm going to go ahead and cut that into fourths, which makes it 1/16. 1/16 is hardly anything at all. And then if I go ahead and cut that into fourths, you'll notice I'm really just multiplying the denominator, the bottom here, by 4. I get 1/64. Think about it. If you had one cake, you had to divide it between 64 people. Everyone's getting a very small sliver of that cake. So it's rapidly approaching this asymptote. Now, in the other direction, instead of multiplying by a fourth, I can divide by a fourth. That's going to be the same thing as multiplying by 4, multiplying by the reciprocal of 1/4. So, to go from 1/4 to 1, you multiply by 4. To go from 1 backwards, you multiply by 4 to get 4. Multiply by 4 to get 16. Multiply by 4 to get 64. Okay, and you'll notice a lot of these numbers tend to match. Anytime you have 1 over as a fraction, the distances have kind of some interesting symmetry almost. So counting from the asymptote, 1, 2, 3, 4. Counting from the asymptote, 16 puts me somewhere up here, a height of 13 roughly. Okay, I would like you guys to write these distances down. That is your work. There's not a lot of work. You don't have to make a table, but those distances tell me that you are thinking correctly. Now we can go ahead. We can put our curve in. This would, again, be decay. 1/4 is smaller than 1. So our domain, our x values here, we are going left forever and right forever. We will continue to get different distances to jump from the asymptote. The range here is not going down forever. It's going down until it reaches this -3 value, which I screwed that up earlier. It's a -2, that's a -3. So we're going to have this natural cutoff. Everything above that is A-OK. It gets graphed there. So I'm going to say from -3 to infinity. Parenthesis on both of them because -3 is unachievable as a answer. So let me show you guys kind of a game that I would play as a kid, and this kind of reinforces exponential growth or decay. So I had a calculator, a little magnetic calculator on a refrigerator, and I remember, and this is a childhood memory, it's a core memory, where I would go into the kitchen and my mom was like getting things ready for dinner or whatever, and she just didn't want to deal with me, and so she would hand me this calculator and tell me, like, sit down, just play with the calculator. And this is before phones or tablets or anything like that, and so this is a big deal for me. I got to press buttons. And so you type in some random number, usually something kind of big or whatever because you were bored, and then you'd stumble across division, perhaps, and you'd type something else in, and you'd hit enter. You'd be like, oh, that's interesting, that's a new number. But this calculator lets you just hit enter again, and it would continue to divide by 2. It would just keep repeating that operation. And so I would sit there and I'd play through my calculator and just divide these numbers up further and further and further and further and further. And I'd start to notice, like, hey, now there get to be more zeros in my answer. And my calculator didn't have this many digits, but you can kind of see that if I sat there for long enough, eventually it gets so small that the calculator can't handle this. Mine goes into scientific notation, but it, for the calculator I had, went to 0. It's like I can't process how small that number is. Okay? And it's kind of interesting to maybe play and see if you can get your calculator to freak out. It's not that there's nothing left, it's just that it's so infinitesimally small that it's basically 0 for all intents and purposes. And you can go in the other direction. So if I clear this out, clear everything here, you can start with any number. You can start with like 3.1. And if you times that, and you just keep hitting enter and enter, you can start to see the answers grow. And pretty soon, on your little calculator, all of the different positions would be full, and there would be no more room for it to calculate, and so it would say overflow. It didn't have enough memory to keep computing things. So you can notice the size of the number that we're getting here, which is crazy, and this is just multiplying by 2. If you go ahead and multiply by something bigger as a base, maybe by 10, it grows more quickly. So there you go. And that's the game that I kind of like to play. I take these distances over here, and I just times them by a fourth over and over and over again. So for example, with us, 64, and divide that by 4 is the same thing as timesing by a fourth. And those are all the distances that we were getting. Okay, 1/64 is 0.015625. Very close to the x-axis. So kind of handy to have a calculator for some of this. Let's take a look at number 5 and 6 and see where these take us. So number 5 is w of x. You can see that there's nothing up here in the exponent position, but there definitely is something here at the end with -8. And that's going to just take us and shift the whole thing down 8. Okay, because we aren't moving left or right, we're just moving down 8. The start of this particular graph is going to be in that location. The starting spot is always impacted by the horizontal and vertical movements, those transformations. What's different and unique about this particular function is that we have a 2 in front. That is going to be my initial value. What happens to that initial value is that it's been stretched. Okay, so that's tying it back in with old transformations. The 3 is not a stretch, it's really my base, it's my pattern. Okay, and so what I'm going to do is I'm going to have to triple everything. Everything triples. So from this star, if I go ahead and I need to count to my first point, it's going to be this initial value of 2. Okay, and the reason is if you put 0 in for its x value, 3 to the 0 is 1. So 2 times 1 gives you 2, and then 2 minus 8 puts you up at -6. And so you can calculate all of these point locations for its x and y values, or you can talk about patterns and how far away from the asymptote you are. Those two things are like heads and tails of the same coin. Now let's go ahead and let's talk about the next distance. Taking 2 and then tripling it based on the pattern leads you to 6. 6 and tripling leads you to 18. 18 and tripling leads you to 54, I believe, and then 54, if I triple that, is 162. I'm trying to do some mental math. Okay, so I'm just multiplying by 3, multiplying by 3, multiplying by 3. Then I go back and I count, so 6 away from the asymptote puts me at a y value of -2. 18 away normally wouldn't fit, but actually since I've been moved down so much, 18 is all the way across the graph at a height of 10. 10 away and 8 away is 18 away. 54 though, no possibility there. So now how do I get the numbers that are further to the left? Well, instead of multiplying by 3, I need to divide by 3. So I end up getting 2/3. 2/3, which would be 0.66666. So a little bit over half of a box. Then I get 2/9, which if you type that in, divide by 3, divide by 3, divide by 3, just like my calculator game. 2/9 is 0.222222. So very close to the x-axis there. Then if I go ahead and divide by 3, I get 2/27, and that's an even smaller decimal amount. And so I'm really starting to approach the asymptote on that left-hand side for this. Okay, going through that initial value, I really start to skyrocket towards some of those higher y values, those heights. Okay, a couple of things maybe before domain and range, and I talk about those. The initial value for this problem was a 2, stretching. This had a growth factor. Its growth factor was 3, so it's larger than 1, it's growing. And then my asymptote here is at y equals -8. You're going to find that wherever this vertical movement is the position of your vertical asymptote. It actually also ties into the range, and we'll see that here in a second. So for my domain, the x values get to move left forever and right forever. There are no x values that do not work in that position. So all reals. If you want to put the infinities, you are more than welcome to do that. Next, the range, the y values. We are kind of capped from going underneath -8. That is not an option. There is nothing below -8. So -8 is the minimum. Infinity, going up, is our maximum. We will never stop continuing upwards with larger and larger answers. Now put a parenthesis on that -8 because, again, -8 as an answer is not something that's achievable. Let's go ahead and let's try number 6. So this problem has quite a bit in it. Okay, the first thing I'm noticing is that there is a reflection. That reflection and stretch both play a role in the initial value that we're going to do. So we can go ahead and write all of that. So this is the initial value. It's how far I will initially jump. It's where I start away from the asymptote for my first step. You can think about it almost like the initials. The initials in your name are the first letters in your name, and this is the first number that's in the equation. After that, I'm noticing 1/6 here. That is my base. Having a base of 1/6 means that I am decay. So this is a decay factor, 1/6 down below. The initial value I could put as -3. And then the last thing that I'm noticing up here in my equation is the +2. It's just going to move me left 2. So no vertical movements, no k value here. Left 2 is the only thing I need to follow before I go ahead and put my asymptote on the paper. Now after this, I need to go ahead and talk about where to start from this star. So initial value being -3, both of those things together. Mean from this star I actually count down 1, 2, 3 positions, 3 units before I put my dot. So in this case, putting your heights above the asymptote is probably a better call. Down 3, and then what am I doing? What's my base say that I need to be doing? 1/6 means cutting into sixths. So everybody is divided by 6, divided by 6, divided by 6, essentially. If I take -3 divided by 6, I get -3/6, which is -1/2. So I cut that into sixths, and I get -1/2 of a unit. Then I go ahead and I multiply that by 1/6, cutting it into sixths, and I get -1/12. That's even smaller. Then if I go ahead and do that again, I get -1 over 72. I'm just taking the bottom and multiplying by 6, essentially. If you want to use a calculator, by all means, use a calculator. So taking 3 and dividing by 6, just understand that it's a negative answer each time. Then, after 0.5, hit that again. 0.08 is 1/12. That's how much that fraction is. Then if I go ahead and take 1 divided by 72, I get this 0.01 number. Just to prove it to you, they're the same number over here on the right. Okay, 1 over 72 and 0.01388888 forever. So these are so close to the asymptote. What if I wanted to go in the other direction? So instead of going to the right and getting smaller, I'm going to be going to the left and getting bigger. So you can multiply by its reciprocal. Multiplying by 6 is the same thing as dividing by 1/6. So -3 times 6 would be -18. Let's see. -18 times 6, really big. or we need to use a calculator. So you could, if you wanted to just stick here, times by 6. And one thing that should actually kind of stand out on your calculator is that every single answer will move backwards, so you're retracing your steps. So there we go with our initial value. There's our 18 that we just uncovered, 108, 648. Okay, so those would be the next distances to the left. Obviously they're growing, or they're coming from very large distances. So 18 away would be all the way off the paper, somewhere down here, most likely. So I can come from that location, very steep, in through the initial value, and then taper right off at that asymptote. So asymptote-wise, this is happening at y equals 0. That's the k value at the very end. Up and down, we don't move up or down at all. My domain, the x values, all real numbers. And then the range here for this one, because it's going down forever towards this point, it will be coming from negative infinity. And then the ceiling of this function is at 0. We do not get answers that are positive in this case, and we would put a parenthesis on 0. If you wanted, you could probably start the homework. You're just going to have to avoid any problems that have E in them because you don't know how to deal with that yet. But whole number wise, if it's growth or decay, that's fair game, and you can get kind of a nice head start on that. But if you have any questions, please let me know. I'd be more than happy to help. Thanks for watching, everybody, and we'll see you soon. Take care.